Howdy, my name is Alex Vogel and I'm part of the Governor Test Stand group. Before we get into the design of our test stand, I would like to briefly go over governors and governor operations so that we have a firm foundation to work from. First obvious question is, what is a governor? A governor is a device, mechanical or electrical, that regulates and controls the speed of an engine. You can think of it, and it is also often referred to as the brain of an engine. So governors operate, you can think of it as a simple input, process, output device. Whereas our input, we have our sensing element, which is going to directly sense the speed of the engine, usually through a connection through a drive shaft. Then that signal is taken to a processor, which is going to take that signal, compare it to a prior set point, and determine an outcome, which will be delivered through an output, which is an actuator that is controlling some device to physically alter the speed of an engine. Usually it's a terminal shaft driving a fuel rack to change the amount of fuel delivered to the engine. So with this, a governor needs to be able to do 5 things. It needs a way to set the speed so we can determine exactly how fast or how slow we want our engine to be running. A way to sense speed, as we said, with our input process, where we get that signal in. Then we need to compare that sensed speed to the set speed to determine if there's a difference. If there is a difference, then the governor is going to act on that differential, and it's going to change the amount of fuel delivered to the engine so that to correct for that change. And finally, it needs a way to stabilize the engine to prevent the engine from constantly correcting itself and getting excessive hunting or surging. So as a basic overview, as I said, there's both electrical and mechanical governors, but I'm going to focus on a simple type of mechanical governor, which is known as the flyweight method. So in this method, we have our drive shaft connected to a system with flyweights and a spring. So as the drive shaft spins, the flyweights swing out and push the summing point up. As drive shaft goes slower, flyweights come in, summing point goes down due to the spring pressure, and this is controlling a pilot valve that's going to control our terminal shaft actuator position, which controls our fuel. Another final important aspect of governors is the concept of speed droop. In this case, speed droop is a percent of change from our set speed that's going to occur as we move from no load to full load. Most governors have an ability to adjust how much droop you have, but it's important to have this setting properly calibrated. If it's too much droop, the engine is non-responsive. If there's too little, then the engine will have excessive hunting or surging. So with all these pieces and components, it can be problems can arise with the governors, and that is where we decided to create our governor test stand in order to address and demonstrate some of these issues.
All right, so as Alex mentioned, there's some aspects that we need to address and demonstrate through the test stand that we fabricated, and mainly I want to cover the highlights of what that test stand does and how it does it. So really, first thing it does, it elucidates the effects of settings and adjustments. So on the UJ governor itself, which is what we test, it has control knobs on it, and setting those, we wanted to visually demonstrate through a live graph what happens to the governor. It also demonstrates, as Alex mentioned, droop in transient loads and speeds, and it delivers a live response over time access from 2 inputs, as you'll see later. We developed a test stand to address 2 key points for TAMU, which is one, as a tool for the MARE 312 Marine Diesels course to help illustrate what a governor is and how it works, and as a base model for future senior design capstones so they can expand and include actuators and PGAs. It's comprised of several components. Main and system components are a table and frame. We used a 24 by 30 3/4 inch flat plate steel, about 40 feet of 2 by 2 1/8 inch angle iron, and a 12 foot, about 12 feet of 5H 5/8" threaded rod, which we use for threaded fasteners and adjustments to individual feet. The main power is comprised of 3-phase 460-volt 3/4 horse motor spinning at, well, we have a range in there driven by VFD, which we'll get into in a second, and about 14 feet of conductor cable ran to a 10-volt and subsequently to a 24-volt transformer. It includes 2 protective circuits, so we did tie in overload protections on those as well. The main power then feeds to a control system after the motor and after the transformer, which is comprised of a P2000 PLC. It's made by Automation Direct, and we tied in a 550 CPU and analog digital module and a high-speed input module, which then feed to the PLC and deliver live feedback responses. Those are sent signals through an optical sensor and a potentiometer, and we again demonstrate the load changes through, as I mentioned, a variable frequency drive. And that's again all to simulate the aspects that was mentioned earlier by Mr. Fogel. And ultimately, we deliver lifetime graphs, as mentioned, through time over a range of values. And we were able to input some of the mathematics into the PLC to range within a pretty close tolerance of each other, so you can see them within one graph at the same time. Thank you.
Howdy, this is our governor test stand. It's built with approximately 40 feet of angle iron. It has a 24 by 30 inch 3/4 plate, a electronic level, so we have a true flat surface, a 3/4 horsepower, 3-phase 480 motor, which drives our governor. Our electrical system is a 480 input, which drives our VFD and our motor. It is then stepped down to drive to 110 voltage to drive our PLC in the back, which has inputs from our optical sensor and our potentiometer, which we use to calculate our displays.
I want to take you guys through the procedure of starting up our governor test stand. First things first, we'll ensure the breaker's off and then plug it into a 480 outlet. Today we're using the one in the machine shop. After that's done, you will flip the breaker on. We have an indicator light to ensure power to the system, and we'll let it boot up. From here, you can see right now this is showing our ladder logic for our monitoring of our speed and our fuel rack position by percentage. From there, you'll come here, you have a run and stop. You will start your press run. That will speed up your motor. And from there, you will click on to data view. And it takes a minute to load up. And here you can see our RPMs. It's to the 10 or times 10. So right now we're running at 1460 RPMs. And from there, you can come here and fluctuate the speed by pressing your up and down arrows to change out your frequency. The higher the frequency, the faster the motor will go. And from there, you can come over to your indicator dials to change different settings. So for training purposes, you can change each setting to show them how the speed and your fuel rack position will change, and also for calibrating to put on an engine. And you're able to mess with speed settings, droop settings, and different things like that to get a change in your fuel rack position. And as you see, as mentioned before, our potentiometer, we have this showing the percentage of what the fuel rack is. as you see, it settle out to about 75%, and with that, you will see that you're getting 75% of what you need fuel-wise.